business like there's no tomorrow.
Congratulations, you have reached the summit of this long journey of 14 lectures. So we have started again from this base camp. We have learned a lot about the filtrations and measure changes. We talked about HJM Merton, so the framework, generic framework for interest rates. And we discussed different models there, what are the beginnings of the development of the interest rate world and how this evolved until today. And then we also discussed the yield curve dynamics, short rates, interest rate products that were very important in the construction of the yield curve. Then we constructed a yield curve and also multi-curves. We also have linked the concept of a yield curve in default probabilities. So that was the concept of multi-curves. Then we have the lecture 7, so it's almost halfway, where we talked about the pricing of swaptions, and also we discussed the concept of negative interest rates. So of course those two were actually, we were halfway through this journey. Then number 8, we covered mortgages and prepayments. What are the risks associated with mortgages? How to handle prepayment risks from the financial institution perspective, and what is the connection between risk neutral and real world pricing measures. In lecture number 9, so here we discussed already, we went all the way from interest rates, because of course this is the main subject of this course, the interest rates. Now in lecture number 9, we extended with additional stochastic differential equations, we extended the framework with more asset classes. Of course, ultimately we would like to derive the portfolio, the exposures, XV for a portfolio of different asset classes or products and also asset classes. Of course, for that reason, we also need to know how to define those stochastic models and how to correlate different stochastic differential equations. In lecture number 9, we have extended, we focused mainly on foreign exchange and inflation. So we have taken some stochastic differential equations from the lecture number 9, and we talked about the particular 2 asset classes of interest. Of course, if we have foreign exchange, this means that our portfolio is not anymore portfolio in a single currency, but we may also have trades for multiple currencies. And of course, that's very important from practical perspective. And inflation products can often, or actually are often present in large portfolios. Therefore, this is important also from an XVA perspective. Lecture number 11 was about market models, in particular LIBOR market model and convexity adjustments. So here we discussed why this model is so important, where is the difficulty regarding the handling of this high-dimensional system of stochastic differential equations, what are the measured changes, and how to handle them in order to perform pricing. And then, of course, the last 2, the most challenging parts, were about the valuation adjustments, XVA, and of course, historical VAR. In both cases, we have performed multiple Python calculations, Python simulations. That led us to the overall, we can finalize with the analysis of the results. So I think after these 13 lectures, you are able to implement your own portfolio consisting of derivatives we have discussed in the whole course. And moreover, you can also perform not only portfolio evaluation, but you can do the risk from risk management perspective, value at risk computation, and also some simple XVAs. So that's basically exactly what was the goal of this course. And today is time to summary. Of course, we are not going into details to discuss all the subjects. Let's just go through all the lectures one by one and shortly summarize what are the key elements discussed in this course. Lecture number 2 was about the understanding of filtrations of measures. Of course, the key word here was filtration and measures, and how it is important that in your simulations, you really understand, you put yourself in a proper perspective where you are in time, what things are happened in the past, what cash flows were in the past, what are the cash flows left for the future, and how to think of you put yourself in traveling some kind in time in order to understand what is your composition of portfolio at a given time. And at the same time, it's not only about composition, you also have to understand what are the risks present at that moment, what you observe and what you can actually read from the market, what is stochastic, what is known, and all those elements are very important also. This is why the filtrations and measures are really the fundamental aspects if we talk about simulations of portfolios in time, and also XVA in general, also VAR, when we talk about discounting conditional expectations. And this was covered in lecture number 2. So here we had 3 blocks. We have the first one started with filtrations, some simulation in Python of conditional expectations. What are the benefits of conditional expectations? How you can price options if you have a complicated model involving possibly multiple dimensions, how to reduce that complexity by conditioning by using conditional expectation. This is also what we have done here in a Python, especially in this convergence experiment. In essence, like we have mentioned, we have discussed that in the course, the idea was that if you know something about your model, about stochastic differential equation, for example, that the model would collapse to the simpler case if some of the parameters are, for example, constant, this knowledge you can incorporate in your simulation, and that can be done via conditional expectation. So this was very important exercise to confirm that convergence of our Monte Carlo can be improved. And then we talked about the concept of numerière, therefore tradable assets, and how to change measures. So first we started with Black-Scholes model, so very classical exercise, changing from measure P to Q. And then I have shown you 3 popular changes of measures that we also have used in this course. The first one was the stock measure. Here we discussed how to benefit from measure transformation in order to solve some complicated payoff involving squares of stocks, maybe not really realistic, but I think that was very illustrative how to perform and how to benefit from these measure changes. In 2.9, dimension reduction, so how measure change can reduce the dimensionality. So this was also very much clear. And then, of course, very important T-forward measure. T-forward measure we have used all over the place in the whole course, especially because in the interest rate world, we rely on stochastic discounting, because we cannot, if we have stochastic interest rates, we cannot say that discounting is deterministic. So for that reason, we need to strongly rely on a T-forward measure or measure of changes in general. In lecture number 3, we talked about HJM Merton. So we had 2 blocks about the framework of arbitrage-free short rate models, or actually in general models which are under the HJM framework. Here we defined the instantaneous forward rate and also the conditions that the dynamics of the stochastic process need to satisfy to be arbitrage-free. And that defined the HJM framework. In particular, we discussed 2 models, Oosterlee and White. Those were models derived based on HJM. So we started with HJM, we specified volatility, and then we arrived at those 2 models. And of course, we also performed some Python simulation in both cases, where we compared the yield curve, which was used as an input, and also yield curve as an output from the model. So this was the whole idea of the HJM framework, or the instantaneous forward rate, or this arbitrage freeness, that the model allows us to that output of the curve, the output of the model, is also perfectly calibrated with a yield curve which is used as an input. And this is much different in equilibrium models, where the yield curve is an output, but it also needs to be calibrated. So it's not used as an input, it's just an output of the model. So this was very also illustrative here when we talk about different settings for HJM, what models are beneficial for us, what we as financial engineers, what models we would like to use. So this was lecture number 3. In lecture number 4, we moved towards yield curves and the dynamics under short rates. So we have, in particular, remember we had this nice experiment where we observed Fed fund rates. So let's say the the short rate, or let's say it's maybe their spot rate of interest rates. And then for every realization from historical data, we were looking at the yield curve dynamics. And that kind of experiment, kind of observation from historical data, we were trying to replicate using short rate models and Python simulation. So this was the kind of relation between the two, and this is what we have achieved in this lecture. So here we, in particular, we talk about the yield curves under HJM and also under the full wide model, an extension of full wide model to two factors. So we discussed the motivation that the full wide single factor model has some difficulties if we talk about the dynamics of a yield curve, especially not today, but dynamics as we progress in time. So from the risk management perspective, you don't want to have only those parallel shifts of a yield curve. You like to have much more richer forward curve that is implied from the model, and that cannot be handled by full wide. You have to do extensions by, for example, two-factor full wide model that allows you to some kind of flexibility. So this was also related to the correlations between LIBORs at given time. So tenors, LIBORs with different tenors, under full wide, they are perfectly correlated, and that's the biggest issue for the model. However, it is still, as you remember, this is our fast car. We can arrive to our solution, but not maybe we cannot do big shopping. So this is limitation of that model. In lecture number 5, this was another building block that we have used to for the yield curve construction, but also later to define our portfolio of interest rate products. Here we talked about, with two blocks, about particular interest rate products. So we talked about the swaps, interest rate swaps, forward rate agreements, and then also we covered some volatility products, in particular under the full wide model. So this was kind of a very important lecture because on one side it defined as the portfolio that we will be using in the simulations for our exposures, but also here allowed us, give us some directions towards calibration and options. So because the model, if we choose full wide, needs to be calibrated to the market data, and of course for that reason we need those option prices. Lecture number 6, this was very much concentrated on building of a yield curve and multi-curves. So here we downloaded some market data from the Fed, from the Treasury Department, and then we use this data to construct the yield curve. So this was also very much self-contained. We basically built everything ourselves. So we built Jacobian metrics, we defined optimization routine, we connected the construction of a yield curve to building of calculating of implied volatilities we have discussed already in a computational finance course. And then at the end, we arrived at the curve that was able to replicate the rates given in the market. So that was basically the goal of this lecture, was to build a yield curve. But this is not it. So also we have discussed the different interpolations impact on hedging, why some interpolation routines may be more suitable for you if you, but of course, depending on kind of objective you have regarding to the representation of hedging and also risks of your portfolio. And then in multi-curve part, we linked the risks of default of counterparties to probabilities of default, and then we constructed a multi-curve. So the curve on the top of the base curve, we also constructed, let's say, representing the reality which is currently available in the market. So very practical set. So this is also a very important building block, because this yield curve construction later on we have used in particular extensively in a value at risk calculation. So this was also very important, and also you don't find often in the literature how to build in details a yield curve with such a hands-on exercise. In lecture number 7, we discussed the concept of pricing of swaptions. So around the exotic or volatility products in the interest rate world, and also we have discussed the problem of negative interest rates. I call it a problem because for many years in the past, negative interest rates was considered to be a problem. These days, it is just a reality. So we had a few important subjects, pricing of couplet and floor rate. So this was kind of introduction to pricing of swaptions. We had a refresher on interest rate swaps. But I think by now you are experts, you know exactly what the interest rate swaps are. And then pricing of swaptions, firstly under the Black-Scholes model. So I'll explain you why this is the why we would do that actually. And then we went through this pricing of swaptions under the full white model, and then of course that required so-called Jamshidian's trick, and then we arrived on pricing of swaptions. So there's some kind of, for full white model of pricing, the most important takeaway: you cannot do that directly. You have to do some kind of a numerical technique apply, and then the application of this technique, it's called application of Jamshidian's trick. So this was the problem with exchanging or getting expectation, sum of expectations of sum of maximums and maximum of sum. That was the whole idea behind Jamshidian's trick. And then the second part, we discussed negative interest rates, shifted log normal, shifted implied volatility. So again, very much we move towards practical aspects of interest rates, and these days, let's say, the current market scenarios. And here we have nice representations of the full white. In lecture number 8, so this is the mortgages. So this was a rather big piece of materials, because we discussed different type of mortgages, the problem of prepayments, determinants for prepayments, amortizing swaps, index amortizing swaps. So there was a lot of details regarding mortgages in general, but also the connection between prepayments and actual derivatives present in the market. So that was kind of a very nice element where we were talking about rational, irrational client behavior and connection to market observable quantities, such that trader could use those to hedge those particular risks. So this was also, like I already mentioned many times, this is very fascinating subject, because this allows us to link the risk neutral measure and also the subjective, the real world measure. So risk neutral, real world measure, those are nicely expressed in the context, where you can actually see those problems when we are talking about pricing of mortgages and there is a prepayment risk. Lecture number 9 was about extension of hybrid models, how to include stochastic interest rates. So first we started with a motivation why it is important to have hybrid models, and then we started with a very simple Black-Scholes whole white hybrid, and then we also talked about implied volatility for models with stochastic interest rates. So this was also the important element, how to think about implied volatilities if your model has stochastic interest rates. In Black-Scholes model we have deterministic interest rates, how to handle that case if you have stochastic interest rates. And of course the main message here was that it doesn't really matter what model, what type of rates it had. The most important element was that we are calculating the prices based on a model, and then we use those prices to calculate implied volatilities. So this is the most important message that you also have heard from me many times in the previous course of computational finance. Then we move to more advanced hybrid models, so the ones involving stochastic volatilities and stochastic interest rates. And then I gave you also motivation of using diversification product, how it can be used for how to see the correlation impact, what is the correlation impact on the price of an exotic derivative. And then we move to a Heston whole white hybrid model. In particular, important part was the Monte Carlo simulation for hybrid models. So for models involving multiple stochastic differential equations, how to perform such a discretization, how to perform large time steps simulation. And also here I gave you almost exact simulation algorithm for pricing of a Heston using simulating Heston full white hybrid model. Lecture number 10 was about foreign exchange and inflation. So we defined, so like I mentioned, we know already that foreign exchange and inflation are very much linked. In foreign exchange, we exchange currencies from different economies. And in inflation, so we exchange notionals between different economies, different currencies. In inflation, we exchange between real and nominal economies. So those concepts are very much linked. This is also the reason why those two subjects are put in one lecture. Again, we define some in the foreign exchange contracts, cross-currency swaps. So this is important product for building of a portfolio. Then pricing of FX options. Again, very important element if we talk about the calibration of the model, because we need to get those volatilities and model parameters from the market. This is why those options are very important. And then I explain you the problem of a Heston model, what type of problems you may encounter if you perform measure changes. If you have Heston model, especially if you have stochastic interest rates, then you will see that there is some kind of correction, convexity, we could call it quantum correction that needs to be included in the dynamics of the model. In the latter part, we discuss the inflation. What are the, let's say, first evolution of inflation over time, and what are the standard inflation contracts available in the market. Those two categories made our portfolio much richer because we were not only looking at the interest rate and maybe stocks, but now we are also able to cover foreign exchange and inflation. This means we are almost covering all the asset classes that you can think, or majority of different products available in the market. So this is, at this point, we are able to construct a portfolio which is very much realistic. In lecture number 11, however, we moved to from the short rate models, we moved to market models. In particular, we discussed LIBOR market model, difficulties and also big advantages of this model with regards to the pricing of exotic, complicated derivatives. So LIBOR market model is maybe difficult to maintain. This is the same. This is in relation to the Stank photo. However, it is really a solver problem. So if you have a very complicated callable exotic derivative, LIBOR market model is typically way to do it, especially if it is extended with stochastic volatility. However, you can destroy your beautiful machinery if you do approximations like, for example, freezing. So you have to be very careful. Sometimes freezing is inadequate, is a good way to handle, especially if you talk about calibration. But if it's abused, it may lead you really to the severe consequences. So in this lecture, we talked about measure changes, what was terminal measure and also the spot measure. What's the difference between the two, and what is the market consensus or market practice regarding these measures. And then we also extended the standard log normal LIBOR market model with stochastic volatility. In particular, we talked about the Heston model, which wasn't great success. And then we moved to displaced diffusion stochastic volatility that allowed us to have maybe a little bit limited flexibility with regards to skew and smile, but allowed us to have a really elegant formulation for the dynamics of the model. This was because of the zero correlation between LIBORs and stochastic volatility. And the last part of this lecture, we concentrated on convexity corrections. I'm pretty sure now you understand what is the problem of convexities and, of course, how to calculate them, because this is what you need to know as a financial engineer. The main objective of this course was the calculation of exposure, XVA, and also calculation of value at risk. In lecture number 12, we have discussed the calculation of exposures and also XVA. So it's also one of those longer lectures where we had 3 hours of 3 blocks of materials, where we discussed the basics behind the XVA or CVA in particular, exposure and potential future exposures, expected exposures. We also explain you what is the idea behind looking into the closed form solutions for expected exposures. And then we also did some Python coding. So here in this Python code, we really constructed a portfolio and we calculated exposures based on that portfolio and 1D risk factor. So we had the interest rate in one currency, we simulated this interest rate, and then based on that, we could evaluate exposure profile for our portfolio of swaps. And then extension to multi-asset, so how to extend the code such that we can handle multiple assets from different asset classes. Of course, calculations of exposure is just a building block for XVA, and this is what we have done later. So we defined, or actually we started from very basic step, how to derive CVA. This was related to the default probability of a counterparty. And then in practical approximations, so this is what often we can see in practice. And then extensions to BCVA. So as you remember, it was a rather trivial extension. And this was related to the symmetry of the pricing. So if we include the counterparty's probability of default, it is then if the counterparty doesn't include mine, we may, or includes mine, we may have a misperception or misagreement regarding the price. Therefore, we have to include the counterparty's probability of default, and counterparty needs to include ours. So the price of derivative needs to include both ours, probability of default, and also counterparties. And that led us to the so-called BCVA. Then, of course, an additional extension was the funding value adjustment, where we could reuse everything what we have learned in this lecture for this FVA. The final part was about trade attributions, so how to decompose a CVA into CVAs of individual trades in a portfolio. So that was also very much practical and driven by the industry. In lecture number 13, which was the final lecture of this course, except maybe for today when we summarize everything, this lecture concentrated on value at risk in the context of historical value at risk, so stress also value at risk, and also Monte Carlo based value at risk. And then we also discussed expected shortfalls. So those two topics, in the first block, we concentrated on the theoretical aspects of value at risk and motivation behind it. And then in the second part, we performed a number of experiments. So first we did a historical VAR based on market data we have downloaded from the website, from the Treasury of Department of Treasury. And then we used that to calculate value at risk. And then further, we also have given you some ideas how to handle what kind of problems you may encounter in practice regarding arbitrage, missing data, and possibly regrading of your yield curve. And then the second part here, let's say the 13.6, VAR calculations for Monte Carlo, which was also an important subject. And I also confronted this measure to the historical VAR calculations. And then finally, backtesting, which was approached to measure the quality of our VAR calculations. So this is it. So this is basically, we are on the top of this mountain. We have reached this. I hope you have enjoyed the whole sequence of this lecture. So we had 14 lectures, including today's lecture. But I think it was worth, because now we have went through all this effort to get to the top, to get to the summit. And I'm pretty sure that you have, if you are here, if you're listening to this, I'm pretty sure you are really satisfied, because now your knowledge has really grown over this number of weeks. We have been learning, we have following this rather difficult path, however, very much rewarding, because now this knowledge can be really used by you in practice. So again, congratulations, and see you next time. See you in the next course. Bye-bye.